this point in the course, it's a good idea for us to take a step back and talk about something that we introduced way back in lecture 1, which is non-inertial transformations. Now, we can deal with this either in the Newtonian formalism or in the Lagrangian formalism that we've been working in. And in this video, I'll touch a little bit on both. But just right off the bat, I want to remind you of an important fact. Because we know that transformations from one reference frame to another reference frame must have a specific form, we can say some things about what forces must look like in those different frames. So let's first start off with a little bit of recap. Imagine that we have an object following trajectory r a of t in a first reference frame, and we would like to find rb of t. Well, we showed that this can always be written in the following way. A matrix capital R of t, which is a rotation matrix, times RA of t, plus another vector C of t. And this just causes the origin to translate. So I'll say translation of origin. Now, we also introduced the concept of real forces and their counterpart, apparent forces, which are sometimes called fictitious forces, but I'm actually going to stick with apparent here. A real force, remember, is one whose force law we know. We know that a real force comes from some source, so maybe it comes from the presence of a spring, maybe it comes from gravity or tension, some force whose force law, again, we can specify. An apparent force is one that doesn't come from one of these, and therefore it must be able to be explained away as part of the motion of the reference frame itself. All right, so the normal assumption is that in one of these two frames, we know that there are only real forces. We called a reference frame like that an inertial reference frame. All right, so in this case, we could pick either one of these, of course, but I'm going to say that reference frame B is actually the one that has real forces. So I'll say reference frame B is inertial. Now, the typical situation is that we're going to assume either reference frame A here or reference frame B is inertial. In this case, I'm going to assume that it's reference frame B. So I'll assume that this is an inertial reference frame. Great. So I have some set of known forces. In particular, the force on this object will be given by F sub B. And my goal is going to be to find, well, what is F sub A? Let me say goal given known real forces in reference frame B, find forces in reference frame A. Great. All right. Now, we can do this in total generality, and I will do that a little bit later after I hop to the computer. But on the board here, I want to do a special case. The case where R is equal to the identity matrix. In other words, a case where we have no rotation of A with respect to B. All right, so note that this means that RB, I'll drop the argument here, but it is still there, is equal to RA plus C. Good. Okay, now if I want to get Newton's second law in here, what I need to do is take a second derivative of this equation. So second derivative. This implies RB double dot is equal to RA double dot plus C double dot. Great. Remember that C is a vector, but it does depend on time. And so this second derivative does make sense. All right. Now, if I know what the forces are in reference frame B, now I can find what the forces are in reference frame A by just multiplying this entire equation by the mass of our object. Let's call it m. So what this implies is that I'll also move C to the other side. M RA double dot, which is equal to the force in reference frame A, is equal to F B minus M C double dot. Great. Okay, so in this case, what we get is a single new force. What does this force look like? Well, it doesn't look like anything obvious because I haven't specified what kind of function C is. Because of the second derivative present here, this could really look like anything. But a nice special, I should say even more special case, is what happens if C is just an acceleration times time squared. So subcase, let's let C be equal to 1/2 a t squared for a constant a. All right. Well, in that case, we would get that F in the capital A reference frame is equal to F in the B reference frame minus, well, if I take the second derivative of C here, I'm just going to get A. So minus A times M, I should say. Sorry. All right. And what does this look like? This looks like the addition of a gravitational field, like the one we experience near the Earth, which is constant. So in this case, we would see objects moving in parabolic arcs or something like that. Let's look at an example where this might be useful. Imagine that we have an object, maybe it's a rocket ship, and it's accelerating upwards with acceleration a. Now I can let one reference frame be the reference frame of the ground. So let's let reference frame B be the reference frame of the ground. And reference frame A, use another color here, is the reference frame of the rocket. Now imagine that there's a person in here, and this person drops a ball. All right. So what happens? Well, we find the following. First, we're going to need to figure out the relationship of the B reference frame to the A reference frame. But that's relatively easy because the A reference frame follows the trajectory of the rocket. So I know that the origin in the A reference frame goes up. So let me maybe draw this out. After a time t, here's the origin of A, of, I should say, reference frame A. Here's the origin of reference frame B. And so if I have some point, let's say right here, then this point has, I should say this length here is 1/2 a t squared. Let me use the vector also, just so that I can be as general as possible. And so the coordinate in this reference frame, if this coordinate, so the coordinate in, actually, I guess I want to go from A to B. So let's suppose that the coordinate here is YA, which we see is negative. We know that the coordinate here, YB, must satisfy the following. Pretty clearly, we have YB minus ya, because remember ya here is negative, is equal to 1/2 at squared, where now I'm just using the magnitude. And so this gives us the relationship that we want. R b of t is equal to r a of t plus 1/2 at squared. Good. All right. So we get exactly what we had over here, that f in the A reference frame is equal to f in the B reference frame minus minus m times A. Good. Now, I'm imagining that this is a rocket taking off from the surface of the Earth. So I actually know what the reference frame, or what the forces in reference frame B are. The only force that's relevant here is the force due to gravity. So in this case, would be just gravity. And so if that is the case, I have that FA is equal to m times minus g in the y hat direction, if I'm imagining that this is the y direction, minus a in the y hat direction. So notice that this builds up to a stronger force. Minus m g plus a in the y hat direction. Good. And that intuitively makes sense. If this rocket is accelerating upwards with constant acceleration, and I drop a ball inside of it, to me, the ball looks like it falls to the floor faster, because from the perspective of the ground, the rocket's floor is rising up to meet the ball. All right, this example takes us through basically what I wanted to do about this case, where we only have C. I'm going to hop to the computer so that we can do this slightly more involved case in which we also allow rotations. I'll see you over there.
All right, now we've dealt with the case in which the only thing that's happening is that the center of mass of coordinate system A is moving with respect to the center of mass of coordinate system B, but otherwise their axes are aligned. We'll go now to the general case and see what we can do there. All right, so we proceed in the same way that we did in the former case. What we're going to do is take a second derivative. But here, we're going to need to be a little bit careful about this matrix R of t. So I will proceed, and then we'll kind of think about this after we've done a couple of steps. All right, so we have RB double dot of t is equal to, all right, so we'll need to take time derivatives carefully. Here we'll have the product rule. I should mention that, of course, R of A also depends on t, sorry. All right, so we'll have R double dot of t will be the first term times RA of t plus 2, because the cross terms, there will be 2 of them, R single dot of t, RA dot of t plus R of t, RA double dot of t plus C double dot of t. Good. So if I want to know what the forces are for RB double dot, I can just multiply this equation by m. So we get mRB double dot. Let me drop my t argument as well, just for the sake of preserving space, is equal to R matrix double dot. Forgetting an m immediately. Sorry about that. mR double dot R A plus 2M R dot matrix R dot A vector plus M R matrix RA double dot plus MC double dot of t. Now, I'm going to give what I hope is a reasonable explanation for why we don't need to deal with this term at this point. The answer is that we can always deal with transformations in two steps. In the first step, we go to a transformation, or sorry, we transform to a reference frame which is just rotating and isn't changing the position of the center or of the origin. In the second step, we now don't rotate and we only change the position of the origin. So what I'll say now is we're going to ignore, we're going to ignore this for now. All right. The last thing to mention is that this, or I should say the last thing before we start thinking a little bit more critically about our matrix, is that this is just our matrix times F in the A reference frame. So this is the force in the A reference frame. Effectively, we have two new forces. And I'll put new forces because in a certain sense, they're not new. They're just from the fact that we made a non-inertial transformation. Okay, good. Now, we need to deal with our R matrix. The reason is that we don't know what this thing is, and so we can't take time derivatives. So let me say how to take time derivatives. And that is a really pretty interesting question. So we're going to use a technique that we learned way earlier in the course, but I was getting ready to be able to use now. And that's the fact that because R is a rotation matrix, it definitely has non-zero determinant. In fact, its determinant is plus or minus 1. If it's a rotation that preserves orientation, which is what I'm assuming for the most part, then it has determinant 1. So may assume it has determinant 1. Now what this means is that I can express R as the exponential of some matrix A. So R is equal to e to the A. Now this is really quite useful because we are a lot better at taking derivatives of exponentials than we are of taking derivatives of other functions. All right. A is called a generator of rotations. And these generators are quite useful because whereas describing the set of all possible rotations in some number of directions is really challenging, there are a lot of different ways that rotation matrices can look. It turns out that describing the set of A matrices that generate rotations is quite a lot easier. So in particular, it turns out every antisymmetric matrix, is a generator of rotations. Great. So what this means is that if I take e to the, for example, e to the 0, 1, 2, minus 4, minus 1, so just to go down this column, minus 2, 4. Now I need zeros, I know, on the diagonal. Then maybe this could be an 8 and a minus 8. This could be a 3 and a minus 3. And this can be a 5 and a minus 5, is a rotation matrix in 4D. Okay, now, why am I doing this? Well, describing the set of antisymmetric matrices is obviously quite a lot easier than describing the set of rotations. So that's really the point that I'm driving at. Now we're not quite out of the woods. Suppose that I want to take d, so let me say just r dot. I know that this is equal to d dt of e to the a, where now a also depends on time. But this is not equal to a dot e to the a. So this is a problem, because that would really make our lives easy. The problem is that it may be the case that a dot does not commute with a. Let's see why that's a problem. So if I start here and then I explicitly take this time derivative by expanding e to the a as its Taylor series, I can see what the issue is. This is a to the n over n factorial. So I can pull that d dt inside of the sum. And by the product rule, what I'm going to get is a bunch of a's multiplied together. Let's say that this is m a's, then an a dot. Let's not forget my 1 over n factorial. Let's do that right away. And then a bunch more a's. In particular, since there were n to begin with, this number is n minus m minus 1, because this is the extra 1. Okay, but anyway, the point is that I can't always pull this a dot here all the way to the left, because it may not commute with a. But if it does commute with a, then I'm good. So to simplify the rest of our calculations, assume that a dot commutes with a. All right. Now let's go back to the actual equation that we are trying to deal with, namely this one, but again, we're going to ignore that last term. All right, so let's copy. Okay, so let's replace r by e to the a in all cases. So we'll get m times d squared dt squared of e to the a times ra plus 2m e to the a. Sorry, before we go on, actually, I'm going to assume that a dot commutes with a and a double dot. commutes with A and A dot. That'll become important here in just a second. All right, in any case, let's keep going. So we'll get 2m ddt of this times r sub a. Oh, my naming convention is maybe a little bit unfortunate here, but I think we're just going to have to trudge ahead. Just note that this A names the reference frame, and this A names the generator. All right. Hopefully it won't be too confusing because this A has the 2 underlines under it to show that it's a matrix. All right, let's continue. So then we get plus m e to the A matrix r a double dot. Good. And we'll begin pulling things down. So, okay, in this case, we just worked out what we get. We get A dot e to the A. But that tells us what's going to happen in this case. By the product rule, we're going to get A double dot e to the A plus A dot squared e to the A. Good. Okay, let's keep going with this computation. So we'll get m A double dot e to the A times r in the A coordinate frame, or the A reference frame, plus 2 times m times A dot, I forgot my second term, oops. So then plus m A dot squared e to the A times r in the A frame plus 2m A dot e to the A ra dot plus m e to the A ra double dot. Great. Okay. Now we can group all the terms that involve the same power, or not the same power, the same order of derivative of RA. So we have these two terms that depend on the 0th derivative. This term depends on the first derivative, and this term depends on the second derivative. Okay. Once again, actually, let's take that second, or that last term, this one, and note that it's just the rotation, e to the A, of mRA double dot. So this is, in fact, that first term, if I pull it to the front, is just R times FA. Good. Now I have plus, let me actually go just in perfectly reverse order. I'll do this term next. So that gives me 2m A dot times R, the rotation matrix, RA dot. Good. Then we get two terms together. We'll have m times A double dot plus A dot squared times R times RA. Good. And so, because on the left-hand side, what we really have is F in the B reference frame, we now have a relationship between the forces in the two reference frames. Now, at this point, it's a good idea to name our forces that we've come up with. Obviously, this is our original set of forces. So let me switch to blue. This is our original set of forces. This is a new force, and it's called the Coriolis force. The thing that's characteristic about the Coriolis force is that it involves the velocity, r dot. Good. So that would be the way that you remember it. The next force is this one. So I'm going to separate these two terms. This one is the next one. This force is called the Euler force. And the thing that is distinctive about the Euler force is that it's the one that depends on the second time derivative of the generator. The last force, this one here, is one that you probably know, although you may not have seen it in this form. This is a centrifugal force. All right. Now, sometimes you will see a specific presentation of these in 3D. So, specific case. 3D with constant rate of rotation. All right, so let's think about what's going on in that case. If we have a constant rate of rotation, then we have r is equal to e to the a, and that in turn is going to be equal to e to the t, let's say, times some constant thing. So let me call that maybe the matrix omega. Okay, and then that will be multiplied by t. So this is how I express constant rate of rotation. A constant rate of rotation will happen exactly when what I have up here is a linear function of t. Okay, so now in this specific case, let's check what we get for r dot. Well, just by the chain rule, I get omega times e to the omega t. Now remember, we were all concerned about whether or not a dot commuted with a. In this case, our a is equal to omega times t, and our a dot is equal to just omega. And these definitely commute. Additionally, we have a double dot is equal to 0. Okay, and that will become important because it means that there's no Euler force. Good. Okay, so let's start plugging some stuff in. So I'll keep this all on the same screen. Okay, so we have FB is equal to RFA. Oops, that's not just a vector, not a matrix. Plus 2m. Remember, a dot is omega times r of ra dot. Good. Plus no Euler force in this case because a double dot is equal to 0. So we just get m times r of a. Good. Sorry, times a dot squared, which is omega squared. There we go. All right, so in some sense, we could say, well, we're done, nothing else to do here. But actually, there is some more that we can say. One thing is that in this case, R commutes with everything, so we can pull R just all the way to the left-hand side. So let me actually do that. So we'll have R of FA plus 2m omega RA dot plus m omega squared times RA. Okay, now recall from above, omega is a 3 by 3 antisymmetric matrix. In other words, we have omega is equal to 0, omega 1, 2, omega 1, 3, minus omega 1, 2, 0, then omega 2, 3, minus omega 1, 3, minus omega 2, 3, 0. Good. And we found earlier on that multiplying an antisymmetric matrix in 3 dimensions by a vector is like taking a cross product. Or it's not like taking a cross product, it has the exact same effect. Omega times, let me just say a vector V is equal to, let me say omega tilde cross V for some omega tilde vector in 3D. And I want to make just doubly sure that I mention that this needs to be antisymmetric. Okay, we found that this vector will be minus omega 2, 3 plus omega 1, 3 and then minus omega 1, 2 as its 3 components. Good. Okay, so actually we can go back here and rewrite these equations if we want. We have that FB is equal to, well, our rotation matrix times FA plus 2m omega tilde cross RA dot. Now for this next term, we have omega squared. What that is going to involve is taking the cross product twice. So then I would have m times omega tilde cross omega tilde cross RA. Okay, so this is an equation that you will very often see that now has our Coriolis and centrifugal forces in sort of a different form, just recast. Let me again note that this is our Coriolis force, and this is our centrifugal force. Great. Now, let's finish off this section of our discussion with an example. Let's imagine that we have a sphere that's rotating around its equator. And it's rotating with constant angular velocity omega. Good. And let's imagine that we just, maybe we throw an object. So we're on the surface of the sphere. Maybe we're at the equator just to make our math as simple as possible here. and we throw an object. Okay, let's figure out instantaneously at the point where we throw this what the forces on the object are. Okay, so in the in the B reference frame, the only force that I'll have is the force of gravity, let's say. So I'm going to imagine that this sphere is a planet. This isn't particularly important. I just want to note that F would be the force of gravity. So FB is the force of gravity in that coordinate system. Now notice that in the original coordinate system, the sphere is rotating. So let me say the sphere is rotating in the B coordinate system. Or in the B reference frame, I should say. Good. So what is the position of the person in the B reference frame? So position of person in B reference frame. Let me, just to not confuse it with the trajectory of the ball, let me use a different variable. Let me maybe say U. So we can still use spherical coordinates in this coordinate system, and the person is right on the equator. So the person's spherical coordinates will be U sub R is equal to capital R, where that's the radius of this sphere. U sub theta, well, that's pi over 2 because we're at the equator. And then phi, well, that's omega times t. Oh, sorry, U sub phi is omega times t. Good, because the person is rotating. Now, in reference frame A, that's the reference frame where the person is stationary. Great. Okay, now let's compare at a vector level what's going on in these two reference frames. Okay, the position of the, or I should say, sorry, the force on the object after it's thrown in reference frame B is central. It goes toward the center of the sphere. So it's always in the R direction, so the R hat direction. Okay, so FB is equal to whatever its magnitude is, we're not particularly concerned with that here, times the BR unit vector, so in the radial direction, right? Its force of gravity is pointing that way. So what this R over here tells us is that we need to first, if we want to sort of imply that this is one of the forces that our object is going to feel in the A frame, or in the A reference frame, we need to rotate it correctly. So in the A reference frame, this is always, so the position of the person, maybe I should have noted that, in the A reference frame is always going to be U, so maybe I should superscript these with B's. Here we'll get UA of R is equal to R, same as before. U theta A is equal to pi over 2, again, just as before. But UA phi is equal to 0. We're always at phi equals 0 here. Okay, so the point is the first term here is the one in which I rotate the correct amount. So I'm rotating about the z-axis by angle minus omega t. So let me say that. So f of a is equal to r inverse f of b. The next term that I need is to take the negative of this to be my Coriolis force. So I have minus 2m omega tilde cross Ra dot minus m omega tilde cross omega tilde cross Ra. Okay, so this vector here always acts in, well, in this coordinate system, the person is always standing straight up on the x-axis. So this always acts in the x direction, really in the negative x direction after the rotation. So in this, draw another picture. In this reference frame, so reference frame A, the person is standing not just on the equator, but on a single point that never moves. Good. And throwing the ball, let's say, in that direction. Okay. So now we need to deal with the fact that the ball is moving and then, use that in the rest of our calculations. One thing that we can do that will really help us out is figure out what omega tilde is. Okay. So omega tilde involves a rotation in the z direction. And so it's just going to be, a vector that only has a z component. So omega tilde is equal to 0, 0, omega. Good. Okay, now I wanted just the instantaneous force. So the instantaneous direction of travel in the A reference frame of this object is the minus theta direction. But if I want to think about that in x, y, z coordinates, that is in the positive z direction. Okay, so let's actually come down here a little bit. We'll just take this equation and start expanding it. So we have FA is equal to minus whatever FB was in the x hat direction, then minus 2m omega, so I can say this is also omega z hat. So omega z hat cross RA dot, let me just say we threw it at speed v. So v in the z hat direction. Good. And immediately we notice that this is 0. So I've chosen a direction for throwing the ball such that we experience no Coriolis force. Very interesting. Okay. Next, I have minus m times omega z hat cross omega z hat cross RA. Now again, just instantaneously, this is the vector capital R times x hat. Z hat cross x hat is y hat. So this gives me minus FB x hat minus m omega, okay, z hat, we'll keep that for now. Actually, let me pull out all my constants. M omega squared r, z hat cross x hat, which is y hat. But in turn, this is going to give me plus m omega squared r x hat, because z hat cross y hat is minus x hat. All right, so in this case, I found that there is a centrifugal force on the ball pointing this way. Okay, what about a second example? I'm going to take the same physical setup for the most part. Except now, instead of throwing the ball up, let's have it thrown into the board. So in the positive y direction, v y hat. Okay, I'll have FA is equal to minus FB x hat. That hasn't changed at all. Now I'll get minus 2m omega z hat cross vy hat minus, same as before, m omega squared r x hat. So this has not changed at all. Plus m omega squared r x hat. So because the centrifugal force only depends on where you are relative to the axis of rotation, the centrifugal force doesn't care that we changed the direction that we threw the ball. Okay, but the Coriolis force does. So let me group all of these x terms. So I have minus FB plus m omega squared r times x hat. And then z hat cross y hat is minus x hat. So that's going to flip this sign, plus 2m omega v x hat. So in this case, all three forces point in the x hat direction. And so we get an even larger force in this direction than we did before. But note that if I change my v so that it's negative, in other words, if I throw the ball out of the screen, then this force actually will cancel part of this net centrifugal force, or net force toward the centripetal force, be that as it may. All right. Now, this is mostly all that I wanted to cover in this general setting. Let's continue with a couple of examples back on the light board.
Before we move on to work out a couple of examples, I actually want to show you how you get all of this machinery back from the Lagrangian formulation, just as you would from the Newtonian formulation. Now, in the Newtonian formulation, we take second derivatives in order to get down to forces. For the Lagrangian formulation, working in rectangular coordinates in both reference frame A and B, I can move between them in the same way that I know how to, just by using generalized coordinates. That will involve taking one derivative of this equation and then plugging it in. So again, I'm going to assume that reference frame B is the one with real forces that I know. So let's take this equation and take one derivative. So I'll have RB dot of t is equal to R dot of t. I'm not going to use the generators here. I'm just going to leave it in this form. Actually, let me also, just to save board space, drop my t arguments. Okay, so RA plus RA dot plus C dot. Good. Okay, now the Lagrangian in reference frame B is equal to 1/2 m. Let me say RB dot RB dot to show what's going on here. Then minus, I'm going to just say U of RB. All right. So we're not going to really be able to do very much with this potential term, which is unfortunate, but there's nothing more to say. Okay, for this first term, however, we can do quite a lot. All right, so I'm going to point out the following. LA is going to be 1/2 m. Now, instead of the dot product, I'm actually going to re-express this in the following way. Let's note that the dot product of two vectors is the same thing as what I would get if I took the transpose of the first vector and simply multiplied it by the second vector. All right. Now, that's going to help because I have a matrix equation above. So let's see what I get. When I take the transpose of the first thing, remember that the transpose flips the order of vector matrix multiplication. So I have RA transpose times capital R, rotation matrix, plus C transpose. Okay, that's my first R dot. Now my second one, I'm going to get capital R times RA. Oh, and of course I need to be using the first derivative here. Correct that mistake before I go any further. So I'm actually missing a term. Okay, this should have been R dot. Then we get RA T dot capital R matrix. Next, we get plus C dot transpose. Great. Now for the next vector, for the vector, not the covector, I'm going to get R dot times RA vector dot plus R matrix times R A dot, times, okay, I have an error here. This should have been just RA, then this is RA dot, good, plus C dot, good. Okay, and before I move on, I need to make one small correction. These matrices need to be transposed. Now, to proceed, I need a really important property of rotation matrices. So, note for a rotation matrix R, I have the following. R transpose times R is the identity matrix. In other words, R transpose is the same as R inverse. Okay, now, before we go on, let's make the same assumption that we did before. Also, assume that R is equal to e to the A, and A dot commutes with A. This is important because now when I take the time derivative of R, as before, I get A dot times R. Great. Now the other thing that I can say is that I have R dot transpose is equal to R transpose A dot transpose. But there was an important thing about A. Recall A is antisymmetric. Now, if this matrix is antisymmetric for all time, then that means that this is also antisymmetric. Great. So I actually can take this equation down here and replace A dot transpose with just minus A dot. So I get R transpose A dot. Good. Okay, now let's take all of that and reduce this. And of course I've forgotten my U. So let me just say U of, well, RB written in terms of RA, which is, I need to subtract over the C and then multiply by R vector or matrix inverse. Oh, I'm sorry. No. Also, before I move on, I realized I forgot to include my potential term down here. So I'll just say minus U of capital R, RA plus C. Good. Okay, now let's move on here, because really the goal here is just to multiply out this kinetic term. Okay, now let's write LA. And really what we're trying to do mostly is just multiply out this kinetic term. Okay, so I have 1/2 m times RA transpose. Now I have R dot transpose times R dot. I'm also going to need the fact that I could write A dot either to the left or right of R, and similarly over here with R transpose. Okay, so in this case, I'm actually going to want to write A next. So this actually gives me a minus, because of this minus sign here, A dot R transpose, but R transpose is R inverse. Good. Then times R, again, I'm switching the order here, but that's okay because of this assumption, times A dot times RA. Good. That's our first term. Next term, I'm going to have this times this. So that is going to give me minus RA transpose. That minus sign is going to come from the same thing here, A dot R inverse. So notice I'm just writing exactly this first part here. Next, I have R times R dot. So R times RA dot. Good. Then lastly, for those terms, I have minus RA transpose. Again, just writing the same first three factors, R inverse, times, well, in this case, it's just C. Okay, great. Next three factors. So first, I'm going to have RA transpose times R transpose, times R transpose, but remember that that's R inverse, times R dot. I'm going to write R dot the same way that I did up here, as R A dot RA. Good. Then next, I have this times this, which is just RA transpose R inverse times R dot, times RA dot. Good. And then lastly, this times C. So then that's plus RA dot transpose times R times R inverse, times C. Great. Okay, then lastly, I have all of these terms. So I have plus C dot transpose. R dot, recall, is RA dot R. RA, RA dot RA. Good. Plus C dot transpose times, well, the same thing that I had here, RA dot. Good. And lastly, C dot transpose C. And these should have been C dots. Apologize for that. C dot. Great. And then minus U of what's down here. I'm not even going to write it out just because this is going to take up enough space as it is. All right. Now we see a lot of nice cancellations of r with r inverse. So here we get a cancellation, here we get a cancellation. Not here, but here we get a cancellation, here we get a cancellation. And I think that that is it. All right. Notice we have these all-important minus signs here too. That's going to become important as we go on. All right. So let's keep trying to reduce this a little bit. Notice that our first term is minus RA transpose times A dot squared RA. Good. In our next term, notice we have one RA, well, really an RA transpose, and one RA dot. That's going to be interesting and important as well. So we have RA transpose, A dot, RA dot. Oops, just one underline there. And then lastly, we get this term involving C. Good. Okay, keeping ourselves going, we get RA dot transpose A dot RA. Good. Plus RA dot transpose RA dot. Okay, and then next, this RA dot transpose R inverse C dot. Good. Okay. Lastly, we get C dot R A dot RA plus C dot transpose R RA dot plus C dot transpose C dot minus U of whatever's in here. Good. Now I can finish this off actually relatively quickly, even though it looks kind of like a mess right now, because everywhere I have a vector transpose times a vector, I can re-express that using the cross product, or using the dot product, sorry. So in particular, notice that in this term, in fact, in all of the terms, I can rewrite things using the dot product. All right, so let's do that. Okay, the first term is going to be A dot RA dot itself. Now to talk us through that, notice that I can make one of these into its own transpose at the cost of this minus sign. Okay. So notice the minus sign is now gone. Good. For the next term, though, I can't quite do that. I need to associate A dot with either one or the other. So let me keep or flip the minus sign to a plus sign, and then associate this A dot with the left. So then I get A dot RA dot RA dot. Okay. Next, I have this term. And for this term, I can take everything and associate it, let's say, with what's on the left. Okay, so let me get, this is plus R A dot RA dot C. Good. Next, I have this term. Now, if I'm careful here, notice that I can do something pretty interesting. So I can express this as RA dot, okay, so that's going to be my left vector, and then my right vector is going to be A dot times RA. And this is the first of several terms that are going to combine, such that my total expression is a lot simpler. Okay. Next, I have this term. This is just RA dot dot RA dot. And notice that this is the term that looks like my normal kinetic term for any Lagrangian. Okay, next up I have this term. And here, the only thing that I need to do is make sure that I associate R with this vector here. So I have R times RA dot C. Okay. Now we're down here. So we get a plus. In this case, I'm going to associate everything after C dot with what's going on the right. This should have also been a C dot transpose. Sorry about that. Okay, so C dot dot R A dot RA. Okay, and then this term, we're going to do the same kind of thing. So, that was missing a dot as well. Great. So actually, at this point, I can associate these two as well. Good. Okay, now I am here. So I'm going to have C dot transpose times all this stuff, but that's just C dot R A dot. Good. And we see, again, I have set of two, which add. Okay, and then I am on my last term right here. So then I have plus C dot C dot. Great. Okay, and then minus U of, I'll write it out this time, R A plus C. Okay, all that's left to do is combine these. So actually, because this is going to be my final expression, let me rewrite the entire thing. So I have half m times, so some of these things are just going to be squared. So in this case, I have A dot RA, that vector squared. Just to write it in a shorter way than writing out its dot product with itself. Next, I have 2 times this thing. So plus 2 times A dot RA dot RA dot. Good. Now another term where I have 2 copies of the same thing. So 2 RA dot RA dot C dot. Good. Now here, I've already taken up this term. Here's my ordinary looking kinetic term. So RA dot RA dot, or maybe just to make it match this one here, I'll say this thing squared. Okay, now another one where I have 2. So 2 R times RA dot dot c dot. Okay, now this term is already taken up, this term is already taken up, and so it's just my last term, plus c dot, didn't close my parenthesis there, dot c dot, and just again, because I'm normalizing my notation here, c dot squared, all of that minus u of, I'll write it out for good measure, r, ra plus c. Great. And that is as good of a final expression as really we need, because in almost no cases where you're actually working with Lagrangian mechanics are you going to need to do it in this level of sort of complexity. Most of the time, when we're dealing with problems like this, we'll be dealing either with a case like the one that we did on the first board, where we have R is the identity matrix, so then all of the A dots would go away. Okay, so let's just look at those two special cases. So in case one, we have R is equal to the identity. In that case, notice that this term goes away, this term goes away, this term goes away, this term does not go away. So that's our first term that is non-zero. Then we have 2 times identity times r dot dot c. So plus 2 times ra dot dot c dot. I should have said c dot there. Okay, then plus c dot vector squared minus u of ra plus c. Good. So in that case, we get a kinetic term that looks like our old kinetic term, but then notice we have something really interesting. We could have, if our reference frame has a c which is changing in time, a quantity that's proportional to velocity. So this is the kind of thing we've only seen so far when dealing with a magnetic field. But now we see one somewhere else in the wild. We also get this other term, plus c dot squared, that is a term that doesn't depend on RA at all. Okay, so that's kind of interesting. Now for our second case, let's deal with the case that we dealt with on the computer, where we have c is equal to 0. And just for good measure, let's deal with the case in which R is a constant or a constant rate of rotation matrix. So it's going to be equal to e to the a naught times t. Good. This implies that r dot is going to be equal to a naught times r, and there will be no t involved. Great. Okay, so in that case, we have L sub a is equal to 1/2 m. Okay, remember a dot is just going to be equal to a naught. So this is a naught times RA, quantity squared, plus 2a naught times RA dot RA dot. Okay, plus, well, this term is 0 since c is 0. Then we have plus RA dot squared. Okay. Then these last two terms are 0 because c is 0. And then we have minus u of, well, now that's just r of r times RA, I should say. Great. Okay, so once again, in this case, actually, we get an extra term that looks like it depends on the velocity. But in this case, it actually couples as in it's in the same term as one that depends on the position. So that's very interesting for us. In any event, we've seen now that we can use the methodology of generalized coordinates to rewrite any Lagrangian where we knew in one reference frame what the Lagrangian was as a Lagrangian in a new reference frame, even if the transformation between reference frames is non-inertial. Now let me clean up the board so that I can take us to a couple of examples before we end. All right, I've collected everything we've derived so far here on the left side of the board. Note that on the last board, I was using A naught, and I actually haven't corrected it in this line, but I'm going to switch that to the same notation that I was using on the computer, where this, instead of being A naught, is omega. Good. Okay, so now let's do a few examples to kind of get our feet wet with this stuff. The first one is going to be relatively simple. Imagine that you're a person standing on top of a moving car, and the car is moving with some trajectory ct, where c is in the x direction. So let's say this is equal to c of t x hat. Good. Then you throw this mass m up in the air, let's say in the y hat direction, and it does feel acceleration due to gravity. Now, we know what will happen in the frame of rest of the, also I should say c of 0, when you throw it, is equal to 0, and c dot of 0 is equal to 0. So the upshot is that this mass really is thrown up, just directly up in the air, because initially this car isn't moving. And so we know what its path will be. It will be a parabola in time that doesn't move in the x direction. But this is not what will happen if the ground reference frame is B. This will not what will happen in, this will not be what happens in the A reference frame, the reference frame of the car. So let's figure that out. First of all, we need to relate the two reference frames. So we have FB is equal to, RB RB is equal to RA plus, well, in this case, let's think about it. If the car has moved to here, so let's say that this is where the car is at time t, and this is the origin of the B reference frame, then this is the origin of the A reference frame at time A, at time t. Now here's some point. We'll call this x sub A, and note that it's negative. And then here is x sub B. So note that x sub B minus x sub A, because remember that this is negative, is equal to, well, the position of the cart in B at time A. So it's equal to c of t. Okay, rearranging this, we find exactly what we expect. xb is equal to xa plus c of t. Good. Okay, so that means that we just need to add the vectors. Great. All right, now I don't need to do this problem using Lagrangians, but I will just to kind of demonstrate the principle. So in this case, we'll have LA. We know all of the motion will be in the x and y directions, so let's put that in explicitly. So we have m xa dot squared plus ya dot squared plus 2 xa dot times c dot, and that's it, because note that in the y direction, we have no motion of the car. So c dot y is equal to 0. Okay, and that also tells us what to do with this last term. This is going to be cx, which is just c dot squared. Great. Then we have minus u of ra plus c. But remember that u is the potential in the B reference frame, and that's fixed. That actually just depends on the y direction, but the y direction is the same between the two reference frames. So this is just minus mgya. Great. Okay, now let's solve this. So dLA dxa will be equal to, well, xa appears nowhere, sorry. So that's 0. dLA dya, ya only appears here. Okay, so that's going to be minus mg, nothing to see there. Next, let's do the derivatives. So xa dot. Now something interesting happens because we do pick up an extra term. So we get mxa dot plus, notice this 2 cancels that 2, and we get mc dot. Great. For ya dot, we just get what we would normally expect, just this part. So we get mya dot. Great. So our Euler-Lagrange equations here are, in this first case, we get mxa double dot plus mc double dot is equal to 0. And in the second case, we get mya double dot, because of taking a second derivative there, is equal to minus mg. Okay, so let's just describe the solutions. We don't really even need to go through the process of solving them. This tells us we have normal parabolic trajectory in ya. And that makes sense. There are no new forces in the y direction, since all the motion of the car is in the x direction. Now, in the x direction, if we rearrange this, this tells us that we effectively have a force pointing in the negative x direction. So we have mxa double dot is equal to minus mc double dot. Good. This force need not be constant. It just depends on what this trajectory is. But what we do have is that c dot of 0 is equal to 0 and c of 0 is equal to 0. So why don't we integrate this and see what we can come up with? If we integrate once, we get mxa dot is equal to minus mc dot plus a constant. But if I stick in xa dot at 0, so if I try to solve using an initial condition and evaluate what this constant is, because I threw this right up in the air, and because the a and b reference frames coincide at time t equals 0, and there's no velocity between them at time t equals 0, this constant must also be 0. So this implies that mxa is equal to minus mc, or another plus a constant, or xa is equal to minus c plus a constant. All right. But again, because these reference frames coincide at time t equals 0, this constant is 0. So what we see in this case is exactly the object moving in the y direction in a parabolic trajectory, but in the x direction, moving with exactly the opposite of the x trajectory of the car. And that's kind of exactly what we would expect. Okay, so this provides a nice sense check. Everything works as anticipated. Now let's jump to a second example. Next, I want to deal with one specific situation, which is where we have constant rotation around the z-axis for reference frame A with respect to reference frame B. So let's get that on the board. So here we'll have a fixed set of axes in reference frame B. And then let's get the rotating set of axes for reference frame A. That color's not coming up very well, so let's maybe try green. Okay, good. All right. So this is going to be reference frame A. And here I'm drawing the x-axis in both cases. And we have rotation around their shared z-axis. Great. Okay, now let's look at this. We have RB is equal to R times RA. And in turn, this is e to the omega t times RA. A, as we've seen. But now I want to figure out exactly what omega ought to be. Now, I've worked out before that omega is going to have non-zero entries. Remember that omega is an antisymmetric matrix. It'll have non-zero entries in the 1, 2, and 2, 1 entries. So I'll have omega is equal to some 0. Let's try minus omega, 0, omega 0, 0, 0, 0, 0 for rotation about z. And I want to check and make sure that this is correct, that this gives us the right answer. So to do that, let me note that omega squared is equal to, well, okay, actually, before we do that at all, let's notice that this choice of omega can also be expressed as omega times 0 minus 1, 0, 1, 0, 0, 0, 0, 0. And therefore, omega squared is going to be number omega squared, so like that, and then times minus 1, 0, 0, 0, minus 1, 0, 0, 0, 0, just by matrix multiplication. Okay. Now, the important thing is that this is minus omega squared times something that looks almost like the identity. Notably, it is the identity in this upper block, in this upper 2 by 2 block, and then it has a 0 block down here, if you want to think about it like that. This matrix is block diagonal with that structure. Okay, so when I now take this exponential, e to the omega times t, what I need to do is expand this out in powers. So I'm going to get omega, again, this is the number omega to the j, t to the j, over j factorial, times this matrix to the jth power. Okay. Now notice that I basically get to ignore what's going on in the z direction. The only time, or I should say in the 3, 3 entry, the only time that I get a non-zero entry here, sorry, to the jth power, is if j is equal to 0, since any matrix to the 0th power is equal to the identity. So I know that I only need to pay attention to these entries. Great. All right. Now, if I go one step further, I know I can break this into even and odd cases, and these will behave somewhat differently. Because if I took omega cubed, maybe I should have done that here, I would get a minus number omega cubed times, well, this is just the identity in those first two entries. In fact, what I get is just 0, minus 1, 0, 1, 0, 0, 0, 0, 0 again. So I get minus omega squared, minus negative omega squared times the omega matrix. Great. Okay, so now let's take this expression and pull it up to the top, and we'll finish it off. So I get e to the omega times t is equal to, well, I'll have a sum over evens. I'll do this just as I did before, this part. Now here I'm going to get this matrix to an even power. And I know that for powers that are multiples of 4, I'll get the identity. And for powers that are 4j plus 2 for some, or 4k plus 2 for some k, then I will get negative the identity. So in other words, I'm going to get minus 1 to the j over 2 times the identity. Again, I guess I'll just keep the 0 down here, but I'm not really going to need it. sorry, and then this does not need to be raised to a power anymore. Great. Then I have the odd terms. Okay, omega j t to the j over j factorial. Now for these ones, for the same reason, if I have a number which is of the form 4k plus 1, I know I'm going to get something that looks like this matrix. And if I have something that looks like 4k plus 3, I'm going to get the negative of that matrix. So let me try this, and we'll check and make sure that it's right. J minus 1 over 2 times 0 minus 1, 0, 1, 0, 0, 0, 0, 0. Okay. And I'm noticing here one problem, which is that this has to be j even and j greater than 0. The 0 term I'll have to separate out by itself. What is the 0 term? It's just the identity. Good. Okay, now let's do something somewhat clever. Notice that minus 1 is I squared. So that this whole thing can be thought of as I to the j. Here I said we would check and just make sure that this works. When I have j is equal to 1, notice that I get j minus 1, which is 0, over 2. So this becomes a plus sign. That's what I want. When I have j is equal to 3, I get 3 minus 1, which is 2 over 2. So this whole exponent becomes 1, and I get a minus sign times this thing. That's also what I want. Good. Okay, I'm going to do the same technique here. Just stick in I squared for minus 1. And then this whole thing becomes I to the j minus 1. Great. All right, but now I'm pretty much home free because I can break this up. Let me put my identity over here now. Into my even part, omega j t to the j. Sorry, let me say I omega t all to the j over j factorial times a matrix which now is outside of the sum, 1, 1, 0, plus the sum over all of the odds of, once again, I omega t to the j over j factorial times this matrix, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. But then I also have a 1 over I, because this was I to the j minus 1. 1 over I is minus I, so I can say minus I times this. Now the key is that this series is exactly the Taylor series for cosine, and where I need to include 0 as well. So maybe what I'll do here is I will add and subtract 0. So let's note that this is basically cosine of omega t. We'll fix this j equals 0 problem in the next line. And then this is the Taylor series for I times sine omega t. This minus I then cancels that I and gives us a plus 1. So that's great. Now, what is the term that I need in here to fix this sum so that it is this? It's just 1. So I'll get 1 minus 1 times this stuff. Great. Okay. Now, I can use that to finally finish up my expression. Notice that because of this minus, I'm sticking the plus 1 inside of the sum. Because of this minus 1, I'm going to get a minus 1 times this matrix. And then I'm going to add that to this matrix. So 1, the identity matrix, minus 1, 1, 0. That's the matrix 0, 0, 1. Good. Okay, then plus cos omega t times 1, 1, 0. Good. Plus sine omega t times 0 minus 1, 0, 1, 0, 0, 0, 0, 0. Great. Or all together, I get cos omega t minus sine omega t, 0, sine omega t, cos omega t, 0, 0, 0, 1. Great. This is indeed a matrix that rotates me around the z-axis. And it rotates me such that it takes, and it rotates me such that I rotate forward by an angle omega t. You can check that yourself. Is that what I want? Well, suppose that I have some point, let's say in this plane. Now here you'll see that this angle that it has with the a-axis is relatively small. Notice that that means that the angle that it has with respect to the b-axis is relatively large if the a-axis is rotating, the a version of the x-axis, I should say. So this is x sub b, and this is x sub a. So if the x sub a axis is rotating counterclockwise, in other words, what we typically consider the positive direction, then the coordinates in the b-axis are larger, or the angles in the b-axis are larger than the ones in the a-axis, and so indeed, this is exactly what I want. So this checks out. Great. So this is the matrix that I need for the rotation. This is my R. But that means what I need for my omega is this, anytime I want to rotate about the z-axis. So let's use this omega to come up, or to deal with a couple of examples. I'm going to erase the board and we'll get right to it. All right, let's deal with a relatively classic problem. We'll have an object, mass m, which is on top of a frictionless turntable, which is rotating with speed, angular speed omega. Okay. Now I want to say that the B reference frame is the reference frame of the ground, and the A reference frame is the reference frame of the turntable, which is rotating about the z-axis. So I get to use my results from the last board. Here I have that R is equal to e to the omega t, where omega is equal to 0 minus omega number, 0, omega, 0, 0, 0, 0, 0. Good. Now, I could do this with either the Lagrangian or simply using the forces, but just for a little practice, let's do it with the Lagrangian. Okay, so I'll have LA, so the Lagrangian in reference frame A. Remember, I want to work this out, at least for practice, in the A reference frame, given the B reference frame. This is equal to 1/2 times m times, well, now I need to do omega times RA quantity squared. Notice that omega times RA is not going to care about the z coordinate of RA at all. It'll only care about the x and y coordinates. Let's work that out maybe over here as just a little parenthetical. Omega times RA is equal to 0 minus omega 0, omega 0, 0, 0, 0, 0, times XA, YA, ZA, which is then equal to, well, an omega can just come out. Then I get minus YA, XA, 0. Good. Okay, and then I need to square that. But in this case, notice that squaring it doesn't actually do anything. I'll just still get XA squared plus YA squared. So XA squared plus YA squared. By not do anything, I mean it doesn't matter that we had the Y on top and the X on the bottom. But that won't be true for this next term, because next we need to dot in this vector with RA dot. So that's going to give us what? 2 times, well, first I'm going to just pull out an omega. I'll keep the 1/2 out here. That's okay for now. But anyway, I'll pull out my omega. Then I get minus YA times XA dot plus xa ya dot, okay? And then lastly, I have my sort of term that I always expect, xa dot squared plus ya dot squared. Notice that because we're constrained to move in the z equals 0 direction, we don't need the za dot squared there at all. And then I said that this mass was free. Other than being constrained to z equals 0. Great. Okay, so now we're basically in the realm of stuff that we're very familiar with, just finding the Euler-Lagrange equations. Okay, so I get a couple of terms here. First, I get m times xa. That's from this. Now, I get another one from here, which is pretty interesting. So notice that this 2 and that 2 cancel. So I'm going to get an m omega just to start. Then I get a plus ya, or I get a times ya dot. Great. Oh, and before I go on, I notice I've made a little mistake here. I have an omega that I do not have written in here. That's going to throw off all my units for everything. All right. Good. Now for ya, I get something pretty similar, m omega squared ya. And then here I get a minus sign, so it'll be minus m omega xa dot. Good. Now for my derivatives of the Lagrangian with respect to the time derivatives. So I get 2 terms for each of these as well. The first one is going to be minus m omega ya. And the second one is going to be, oh, and sorry, the second one here in this term is going to be plus m ya dot. Good. Now over here, I'm going to get a m omega times xa plus mxa dot. Great. Okay, so my 2 EL equations are, to combine these two, well, actually, before I go too far with that, I can take a time derivative right away. If I take the time derivative, notice that the only thing I'm going to hit here is the ya, and here I'll get the ya double dot. And screwed this up. That should be xa dot. This should be ya dot. Okay, so I'll get an xa double dot there. Okay, so anyway, I get an mxa double dot. Now notice that I can actually move this to the side once I take the other side, once I take the time derivative, and it'll combine with this term. So I'm going to get that this equals 2m omega ya dot plus m omega squared xa. Notice that I have the exact same breakdown as I thought that I would. Here is my Coriolis term. It matches this. And here is my centrifugal term. It matches this. Great. In the y direction, I'm going to get mya double dot is equal to, well, now when I move this over, after taking the time derivative, it'll combine with this term, but I'll get a negative sign. So minus 2 m omega xa dot. Great. Plus m omega squared ya. Good. Okay, now we could go through and solve these equations, but I really am more interested in qualitative stuff for the time being. Note that here, this was like taking or multiplying by this matrix is like taking the cross product with the vector that we've called omega tilde, where omega tilde is equal to minus omega 2, 3, omega 1, 3, and then minus omega 1, 2. Great. Okay, so in this case, omega is exactly, so here, omega tilde is exactly omega times the minus 1, 2 entry, which is itself minus omega. So this is omega times the z hat vector. All right, now using this result, I want to sort of just see pictorially what direction the Coriolis force should go in. All right, so here we have the Coriolis term, and notice that what it looks like is minus this omega tilde vector cross RA dot, which is like V dot, or sorry, which is like V. So I need to think, I want to take the cross product of omega tilde with RA dot and take its negative. That's the same as taking the cross product of RA dot with omega. All right, so to use the right-hand rule, I need to take a cross product that where my first finger goes in the direction of the velocity, then the second set of fingers goes in the direction of the omega tilde vector, which is out of the board here. And then I curl it to find the direction, finally, of the force, of the Coriolis force. So the Coriolis force, in this case, points in this direction. Notice that, as expected, the centrifugal force always points directly outward from the center of rotation. Great. Okay, now over on this side of the board, we can finish up our discussion by looking at the Coriolis force when we're dealing with objects on the Earth. So in this case, we have a slightly more complicated picture. Here we have a sphere which is rotating. Now I'll put my origin in the center of the Earth, and I'll think of the Earth as being a sphere, and I'll want to deal with a point at a particular latitude. Actually, it turns out that we measure things more typically in terms of theta being the co-latitude, that is the angle between the North Pole and the point in question. Great. We talked a little bit earlier on in the video about what happens when we're on the equator, but we'll see that it gets a little bit more complicated when we're over here at some co-latitude which isn't theta equals pi over 2. Okay, so in this case, we launch a projectile, and we want to know what direction is the projectile going to go. Normally, we would expect that it just goes in a normal parabolic arc, but here things are going to get a lot more complicated. And the reason here is that we still have to take into account both this force and that force. Let's first just think about what directions those two forces go in. We might immediately think that the centrifugal force should come out from the center of the Earth, but that's not right. Remember that it points out from the direction of the center of rotation, which in this case is the z-axis. So actually, the centrifugal force points in this direction. Meanwhile, of course, the Coriolis force depends on the direction that we launch our projectile. We already saw what happens when we launch the projectile north. And the answer is that if we're at the equator, nothing happens. But here at colatitude theta, we actually do get something sort of interesting happening. Remember that to see this, we need to take the cross product of omega with RA dot. Okay, so let's do a couple of examples. First of all, what happens if RA dot is north? So in other words, take the right hand, point it north, and then point omega up. We find that for an object launched north, the Coriolis force comes this direction. Good. Okay. Next, what happens if we launch an object east? if we launch an object east, then we need to do this once again. In this case, we point these in this, or the thumb in this direction, fingers up, and so we get that kind of deflection. Now, one important piece of this, which I think is really important, is that notice that both the Coriolis force and the centrifugal force in general affect the force toward the center of the Earth. So we all experience a gravitational acceleration toward the center of the Earth, but it turns out that that gravitational acceleration is not precisely g, the true gravitational acceleration that we should expect given the mass of the Earth. Instead, it's affected by the radial component of the centrifugal force, which we all feel because we are on the surface of the Earth, and it's also possibly affected by the Coriolis forces. It's just that for ordinary speeds and for the radius of the Earth as it is, those other components of the radial force are so small that we don't notice them. However, if we launch a projectile quite quickly, then we may see the Coriolis effect come into play. So if, for instance, we're trying to launch something hundreds of miles, then the Coriolis effect has a major impact on the final trajectory of the object. A final point about this Earth system is that the Coriolis effect in specific has a big effect on Earth's weather. And that's because even though the Coriolis forces are not that large on the air moving around on the surface of the Earth, the length scale on which we care about weather is very large. And so even small effects have a chance to sort of grow over space. So it turns out that this determines in large part the direction of the prevailing winds on the different hemispheres. Okay, that's enough for this video. In the next video, we're going to jump to a brand new topic. We're going to start talking about the Hamiltonian formalism of classical mechanics. I hope to see you in that one. Hang on, sorry, me from the future. I realized that the light board's orientation problems have caused me to get a couple of things wrong here. I need to be careful. Okay, so if we shoot a projectile north, then I should put my finger in that direction, and then the omega tilde vector points that way. So I get something that is away from the screen for you. So I will write it like this is the direction of the Coriolis force. Great. Meanwhile, if I shoot something to you, it's coming out of the screen, then I should put my finger like that, point up, and then that goes that way. All right. Sorry for the oversight. I'll catch you in the next video.